Okay, let's look at part two. We'll start out with an example of trying to figure out the molarity of a particular substance in coffee. And we know the substance in coffee we're most interested in is caffeine. So, in a 350 milliliter cup of coffee has about 150 milligrams of caffeine. Of course, it depends on, whatever the particular coffee you're drinking. So we want to figure out moles per liter. So if we start with the bit of information we're given, this is happening again, we have 150 milligrams of caffeine. I want moles, so I'll put moles on top, and we look up what the molar mass of caffeine is. And we find the molar mass of caffeine is 194.19 grams. So this will give us moles, but remember we want molarity, and molarity is moles per liter. So I want the volume in liters on the bottom. And if I have 350 milliliters, we know that there's 1,000 milliliters in a liter. So if I divide that number by 1,000, I get 0.350 liters. And multiply all those together, and I get a number of 0.002207 molar. So now I have to look and see how many significant digits I should give. So let's look at the volume first. 350. So 350 is how many significant digits? 2. That's right, it only has 2 because there's no decimal at the end of that. So only the non-zero numbers ahead of the decimal are significant if the 0 is the last one. So that has 2. This has 3 because zeros after the decimal are all significant because they're put there for a reason. So 2 significant digits. So let's look. Here are my 2 significant digits. And when I round that, I'm going to get 0.0022 molar. Also, we can convert that to another unit called millimolar, which just means 1,000th of a molar. So there's 1,000 millimolars in 1 molar. And when we do that, we get 2.2 millimolar. Darn screen. 2.2 millimolar. And you'll see that millimolar a lot when you're dealing with really small concentrations. You'll see millimolar. You will see micromolar, which is 10 to the minus 6 molar. And you'll even see nanomolar, which is 10 to the minus 9 molar. So for really dilute solutions where we're doing reactions and we still need moles, we'll have millimolar, micromolar, nanomolar. So these are the approximate concentrations of some of the solutes we typically associate with being found in the body. You can see that outside in blood plasma, we have quite a high concentration of sodium. But then inside the cells, you're going to see more potassium. So there's an imbalance between the concentration of sodium on the outside of cells and potassium on the inside. So outside the cell, we'll find very low concentrations of potassium at like 5 millimolar. And calcium, magnesium, chloride ion, there's quite a lot of chloride ion in the blood, and bicarbonate ion, which is also used as a buffer to regulate the pH. When we're talking about buffered solutions, we talk about acids and bases in the next chapter. So now is another concentration we need to discuss, and that is something called equivalence. And equivalents are also a molar concentration, but instead of just being any kind of solute, we're talking specifically about charged ones. So an equivalent is a mole of charge. So if I was to dissolve 1 mole of sodium chloride in water, when it dissolved, remember that it dissolves into its ionic forms and separate from each other. And so from 1 mole of sodium chloride, I would have 1 equivalent of sodium ions and 1 equivalent of chloride ions. I would now have 2 equivalents of charge, okay? And when we're diluting these things, we're adding solvent to dilute a solution. We're trying to figure out what concentrations are. Remember, the amount of solute doesn't change. So the number of moles is the same after we've diluted it, before we've diluted it. Because the only thing we've added is solvent. We haven't added any more solute. So the number of moles of solute stays the same. So the only thing that changes is the volume. So the only thing we would change it by is the new volume. So when we dilute something by 2 times, we increase the volume by 2. So if I put a 2 here, then my concentration is now 1/2 of what it was originally. And so just consider the number of moles. So the amount of moles will always be the concentration times the volume. And so the initial number of moles is going to equal the final number of moles. And so we're going to use this a lot to figure out concentrations. Like I mentioned in the previous part, in part 1, in a lot of labs, we have what are called stock solutions of things we use commonly. NaCl, KCl, all sorts of solutions like that we use a lot. And so we would make them in very concentrated solutions. Like let's say we would make like a 2 molar solution of something. But then we wouldn't use that molarity because that's way too concentrated for what we want. Let's say we would want like a 50 millimolar or 0.05 molar solution. Then we would just dilute that with water to the concentration we want. So to determine the concentration after dilution, remember the moles in the beginning, which is the concentration times the volume, is the moles at the end, which is the concentration times the volume. Just the concentration has changed. So if we want to solve for final concentration or we want to solve for final volume, we just use this particular equation and move it around to however we want to solve it. If we want to solve final concentration, that would just be the initial concentration times the initial volume divided by the final volume. And that gives us the final concentration. So for instance, if we have a 0.50 molar heparin solution, and heparin is used to keep blood from coagulating. So if we're worried about blood coagulating too quickly, we include heparin in the solution. So this is our initial solution. We would say this is our stock solution. And then puts that into a 250 ml IV bag, and then you would have a final volume of 255 mils because you have to add the volume of your solution you start with plus the one you've added. So what's the resulting final concentration of heparin? Well, to solve that, we then use our good old C1V1 equals V2C2. So our initial Our initial concentration is 550 molar. And the fun thing, I'm just going to keep putting that C there, and it's going to keep going away. The interesting thing about this particular equation is that we don't need to use liters as a unit. We can use whatever volumes we want, because the volumes will cancel out. Basically, all we want is what the dilution factor is. So we don't have to use liters. We can use milliliters. We can use microliters. We can use whatever volumes we like. We can use gallons if we want, as long as we use the same unit top and bottom. So here's our initial concentration. The initial volume was what the stock solution was in. So in this instance, 5 mils. That is going to equal the final concentration, which is what we're looking for. And what's the final volume? The final volume is 255 mils. So if I divide both sides by 255 mils, the mils cancel, and now the only unit I have left is molarity, right? So this is my dilution factor, 5 over 225, and that tells me what my final concentration will be. And my final concentration will be 0.0108. Oh, sorry, 1078 molar. Now we look and see how many significant digits we should use. I've got 3 significant digits in my initial volume. I've got 3 significant digits in my initial concentration. I've got 3 significant digits in my final volume. So I'm going to have 3 significant digits in my answer. So let's go looking. 1, 2, 3. So I've got an 8 after my last significant digit, so I round up. So my final answer will be 0.0108 molar. Or 1, 2, 3, 10.8 millimolar. Okay? Let's talk about how solutions are actually made. We've sort of talked a little bit about this in the past, but it's basically a 2-step process. The first being solvation. And I sort of mentioned before that when you dissolve a salt into water, that your positive ion, your cation, and your anion, your negative ion, then gets surrounded by water in what we sort of call like a solvent cage. And that's sort of what we see here. You can see here we've got the negative charge. That would be the negative ion interacting with the positive parts, the partially positive parts of the water. And here we would have negative or the positive interacting with the slightly negative side, or the oxygen side. So both of them are then surrounded by water, making these ion dipole interactions, which are really strong. And that's why ionic solutions dissolve. That's why ions dissolve in water in the first place. You have more ion dipole interactions than ionic interactions. And if the multiple ion dipole interactions are stronger than the ionic interaction, then they replace the ionic interaction, and the ionic interaction breaks, and then you get surrounding by the water. So we call that solvation. Okay? So you replace the ionic interactions with ion dipole, 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 and hydrogen bonding interaction. You get all these different hydrogen, like really strong interactions taking place. The second part is the dissolution. That's when, so initially you start forming these ion-solvent interactions, and then basically you form enough of them and you pull the two ions apart. So that's when you get like sodium and chloride completely separating from each other. They say they dissolve, basically, right? That's what the dissolution is. They dissolve. We dissolve that bond. That sodium chloride ionic bond is dissolved. And when that dissolves, it goes into solution, where this interaction is replaced by interactions with the water. Now, those ionic compounds where the ionic interactions are much stronger than potential solvent ion interactions, they're not going to dissolve. So mostly ionic compounds with a lot of charge, like, +3, -3, +2, -2, or ionic compounds like sodium chloride, which is only a single charge, but those two atoms come together really, really close to each other. And so that becomes a really, really, really strong ionic bond as well. When the ionic bond is too strong, then they don't dissociate, they don't dissolve, and the ions don't become hydrated, and you don't get a solution. So these are some of the terms where we're dealing with solutions. One you've probably heard of is an electrolyte. You see these all the time in like Gatorade commercials and stuff, right? To replace your electrolytes. Well, an electrolyte is just an ionic compound that dissolves in water. That's all an electrolyte is. And there's two different kinds of electrolytes. Ones that ionize completely, so they completely fall apart, like sodium chloride. When sodium chloride dissolves in water, you form, like 1 mole of sodium chloride will give you 1 mole of sodium ions and 1 mole of chloride ions, or one equivalent, remember, of each one. Now, a weak electrolyte is something that does not ionize completely. It still dissolves in solution, but it doesn't all become ions. And one of that is acetic acid. Acetic acid is a organic acid that has this group. So when we dissolve organic acid in water, this is where the H plus comes from, but only a few % of the molecules will release that hydrogen and cause the pH to go down. In acetic acid's case, it's only about 0.05%. It's really, really low number. So that it's a weak electrolyte. And a non-electrolyte is something that doesn't release any ions at all. So sugar, when it dissolves, isn't ionic. It's covalent. And so when it dissolves in water, you don't see any ions appearing. So it is not an electrolyte at all. And basically what we call electrolytes is something that can conduct electricity in water. If we were to put 2 wires into water, and could it conduct electricity between the wires? If there's a strong electrolyte in there, it can, because the ions in the water will move to each side of the wire and transmit charge. Strong electrolytes will do that. Weak electrolytes will do it a little bit, but poorly, and non-electrolytes won't conduct electricity at all. So in the medical field, we use electrolytes to mean generally any of the really important ions that show up in blood in the body. Potassium, sodium, calcium, magnesium, chloride ion, the ones that we typically see. So that's what we generally mean when we mean electrolyte in sort of medical situation. These are some of the other properties of solutions. We're not going to deal too much with them. but the ones you probably should be aware of. These are called colligative properties. Colligative properties are just depend on the number of dissolved particles in solutions. It doesn't really matter what the particles are, it's just how many of them are dissolved in solution. One of the effects that has on solutions is the vapor pressure. If you dissolve a lot of something in, let's say, water, the vapor pressure of the water will go down. So we know that at atmospheric pressure, water is being turned into a gas, and also that gas is being turned back into a liquid. We sort of have an equilibrium taking place. We have a certain amount of gas in the air, and we have a certain amount of that gas returning to make water. If we dissolve a bunch of stuff in the water, we have less of that water escaping into the gas phase, because now in that solution, less of it is now water, and so the pressure goes down. We also elevate the boiling point. So if you were to dissolve a lot of salt in water, you would notice that the boiling point is now higher than it was. For pure water, the boiling point is 100 degrees C. If you would have like a saturated solution of sodium chloride in there, the boiling point would be much higher by 10, 20 degrees, depending on whatever the atmospheric pressure is. So it raises the boiling point of water or whatever the other solvent is. The other thing it does is lower the freezing point. And that's basically how Fahrenheit came up with his scale of water, of temperature. He started at a freezing point depression mark. He looked at the freezing point of salt plus water. Why he chose to do that, I can't tell you. Basically, it was brine he was looking at. So brine has a lot of salt in it. If anyone's ever made their own pickles or whatever, it has an incredibly high salt concentration. So brine, the one he was looking at, froze at 0 degrees Fahrenheit. But we know that water freezes at 32. So all of that salt in the water lowers the freezing point of the water by 32 degrees Fahrenheit. Because basically it disrupts all of those hydrogen bond networks that the water makes. And we know that when water freezes, it sort of freezes in place, and we get this particular stacking of water molecules due to the hydrogen bonding between the different molecules. Well, you throw in a whole bunch of salt, you mess all of that up. And so in order for that solid to take place and all these things to remain rigid, it takes a lot lower temperature to lock these water molecules into a particular shape than it does at when there's no salt around. So that's why you will see salt water, like in the oceans. If the oceans, sometimes you see, like where I grew up, the harbor, which was part of the ocean, would freeze if it got cold enough. But it would have to be really, really cold for that to happen. Meanwhile, in the park where you've got fresh water, they would freeze much, much more easily. So if we wanted to go skating in the winter, we would skate on the park ice when it wasn't that cold. And when it got really, really cold, we could actually skate across the harbor, which was a lot of fun. So these are important properties of solutions in the hospital. We're talking osmosis. So osmosis is the process through which solvent molecules can pass through a membrane. And a membrane basically is just something with very, very small pores that allow small molecules to pass through, but large ones can't. And so what happens in osmosis is that water will move. Water is a very small molecule. Water will move to where there is a lot of solute particles to some place, or I'm sorry, where there's a lot of solvent molecules and very few solute particles, to where there's a higher concentration of solutes. So osmotic pressure is the tendency for solvent molecules to move from a more dilute situation where there's less solutes to a more concentrated solution. And they'll keep moving until the concentrations on both sides of the barrier or the membrane or whatever it is are equal to each other. And so that's osmotic pressure. Solvent will move to where we have higher solute concentrations, and we'll keep going until it evens them out. Now instead of talking about just molarity, we're talking about osmolarity. So osmolarity is basically takes into consideration all the particles in a particular volume, not just salts or sugars or whatever, ions, all of them together. We have to take all the concentrations of all the different particles and add them together to get the osmolarity, okay? Because it's the concentration of everything that isn't water on one side of the barrier. So if I have salt on one side of the barrier, if I have sugar on one side of the barrier, if I have ions one side of the barrier, whatever I've got, electrolytes, doesn't matter. If I have higher concentration of stuff, water is going to move to where the higher concentration of stuff is, so that the osmotic concentration is the same on one side and the other. Now, where this becomes really important is in dialysis, because this is what your kidneys do all the time. Your blood will have high concentrations of sugar, well, hopefully not sugar, but salts, wastes, whatever is in your blood that your body needs to get rid of. And so we know that where the concentration is high, solvent will come in and reduce that concentration. So water will move in and reduce the concentration of those molecules, which then get excreted as waste. So that is how our kidneys function in removing waste and extra water as well. When you go to the bathroom, obviously a lot of what you're releasing is water. So in what kind of dialysis? Called hemodialysis. So this is a dialysis machine over here. It basically acts as an artificial kidney. So inside the kidney machine, we have a barrier, we call it dialysis membrane, actually, which allows small molecules to pass through it. So in this instance, not just water, but other small molecules like salts and wastes can pass through. And so the solute molecules will move from where it's more concentrated to where it's less concentrated. And water will do exactly the opposite, moving from where solute is more concentrated to where it's, or less concentrated to where it's more concentrated. So basically they swap places. So hemodialysis then, hemo meaning blood of course, uses osmosis to cleanse the blood of those waste products that the kidney can't do. And so it's really important for them to go to dialysis like 1, 2, 3 times a week, depending how much kidney function there is. So this shows what some of the cells in your body, what will happen to them under different concentrations of solute. So an isotonic solution, as you might know, has the same osmolarity that exists inside the cells. So that the concentration of everything, all the solutes inside the cell and outside the cell are the same. That would be the situation in the middle here. So we don't have a net influx of water into the cell or efflux of water out of the cell. And so the cell maintains the same volume because the amount of water going in is the exact same as the amount of water coming out. And so it retains the same volume. And so we would have a normal looking cell. If, on the other hand, we put it into a hypertonic solution, hyper meaning higher. So we have a higher concentration of solutes outside the cell than inside. So hypertonic, higher concentration of solute outside the cell. Well, what's going to happen? Well, we know that water is going to move from where the solute concentration is low to where the solute concentration is high. And so the water is going to move out. It's going to be an efflux of water out of the cell. And that cell then is going to shrivel up because it's losing water. And this is red blood cells shown over here. And when the red blood cells shrivel up, and eventually they'll die if they lose enough water, we call that crenation. And basically you can see it under a microscope. The cells just shriveling up basically because they're losing volume because of the water leaving them. Now, on the other hand, if we have a hypotonic, hypo meaning lower, we have a hypotonic solution, that, like, just let's say this pure water, meaning we don't have any solute concentration outside the cell. Well, what's going to happen? Water is going to rapidly move from where solute concentration is low, outside the cell, into the cell, where solute concentration is higher. And so the volume of that cell is going to get higher and higher and higher until eventually it bursts, because the cell membrane can't contain that volume. So, like, if you blow up a balloon enough, it's going to pop, and that's what happens. So if you put like red blood cells in just pure water, they pop because the water rushes in to lower those concentrations of solute inside the cell, and that's called hemolysis. And so you see that I used to get a lot of hemolyzed samples in my lab. Like, people would ask me to analyze, plasma and serum samples for various things. And if they gave me hemolyzed samples, I really couldn't use them because the overwhelming protein in hemolyzed samples would be hemoglobin. And if you have a huge amount of hemoglobin protein in the sample, it basically overwhelms everything else, and it kind of makes it hard to analyze. So, and hemolyzed samples are obviously pretty easy to tell because they're red, even when you spin all the red blood cells down. So one of the things you could do where you're really interested in both, once you've figured out all the gas laws and you've figured out, hypotonic, isotonic, perfusionist is one of those things. So it's a medical technician that assists during any kind of medical procedure where breathing functions require support, or circulatory functions, like in heart-lung machines that would operate. Like if there's, heart operation, you have to stop the heart in order to operate on it. So you still need blood to be pumping through. So what a perfusionist does is monitor the heart-blood machine. They're running it and make sure that the oxygen and CO2 levels in the blood match what they should. And so they monitor the machine and the blood status, notifying the surgeon and especially the anesthetist of anything that's going on. So you can change the amount of oxygen, lowering or hiring it, or doing something, adding drugs to change the balance of blood levels of a lot of different things. So that's something you can do with this particular information. And now that you're all experts, I expect you to start doing it. All right. I'll see you on Tuesday.